Hi everyone, hope you're doing well. We're going to get started with Lab 6, which is Metapopulation Modeling. This is a chance to get familiar with classical metapopulation models and some more sophisticated metapopulation models. Classical metapopulations are the models that Gotelli describes in his metapopulation chapter. And we're also going to go a little bit beyond Gotelli to go into some more realistic metapopulation models that you can develop. There is no reason to be constrained to the classical metapopulation model when we have powerful computers and we have our own creativity and our knowledge of programming. So I don't want you to feel limited by that. All right, so let's start with some definitions. We already talked about metapopulation models, so I'm going to go pretty quickly through this, but we're going to start off with really simple models. This is the classical metapopulation models. In this model, in this framework, we're not thinking about individuals. We're not thinking about individual animals. What we're thinking about is patches. Patches are the basic unit of a metapopulation model. We have a bunch of patches on a landscape. These are just potentially habitable units of space that may or may not have the species of interest actually occupying a patch. So patches are either occupied or unoccupied. There's only two possible states for a patch, just as there's only two possible states for an individual in our individual models, live or dead. Although we don't keep track of dead individuals, where we do keep track of dead patches, and that is unoccupied patches. And you'll see that as we go through these models. But the key is that we're not paying attention to abundance anymore. We don't care about the abundance of each patch. We're just keeping track of whether each patch is occupied or unoccupied. We're keeping track of essentially how many total occupied patches we have in our metapopulation, or more specifically, the fraction or proportion of patches that are occupied at any given time. A classical metapopulation is best considered as a population of patches. So instead of a population of individuals, we're thinking about a population of patches. That's where the term metapopulation comes from. Meta just means the next level up. So you take a population, and then a metapopulation is a population of populations. It's just the next level up. A population is a population of individuals. A metapopulation is a population of populations. And when we say a population of patches, we're acknowledging the fact that some patches may not be occupied at any given time. So we can't really call it a population necessarily if there's no individuals in it. Okay, so there's two processes that can change the proportion of patches occupied. We can increase the proportion of patches occupied by colonization. So a patch goes from unoccupied to occupied. That essentially increases the overall occupancy of the metapopulation. And colonization happens through immigration. So there has to be some source of immigrants for colonization to occur. Extirpation is the opposite process. That's where a colonized or occupied patch becomes unoccupied. So sometimes that's just called extinction. We can call it extirpation. Either one, it means the same thing. Now, if all patches in a landscape become extinct, that has a special term, and that's called global extinction or regional extinction. And that's just once that happens, there may be no chance for patches to be recolonized because there's no source potentially of new colonists or immigrants because the whole metapopulation is extinct. All right, so more formally, let's consider the math. Let's do the math. I miss the old cheer I used to get when I used to say that in our live lab period, but I'm just imagining the cheer about the math. All right, so little f, is the fraction of patches that are occupied at time t. This can be called the metapopulation occupancy, and in Insight Maker terminology, this is the stock. This is the thing we're keeping track of. We're keeping track of the amount of the metapopulation that is occupied, or the total fraction of patches that are occupied. And once we start to think about the dynamics or the flows in this model, if F is the stock, what are the flows? Well, the flows are I, which is the total fraction of the metapopulation that's colonized by immigrants in a given time period. So the total fraction of the metapopulation that becomes colonized in a given time period. That's called the colonization rate, or the reason it's an I, and Gotelli uses I, is it can be called immigration rate. I don't like that term because I like to think of immigration as actually individuals immigrating from another patch. It's not a patch becoming colonized. So I like to use the term colonization, but I keep the I because that's what Gotelli uses. Big E is the total fraction of the metapopulation that goes extinct per time period. All right, that can be called the extirpation or extinction rate. And so if you want to compute the total absolute change in occupancy, that can be expressed as delta F is equal to I minus E. And F is the stock, and I and E are the flows. All right, so the question I pose here is, if F is the stock and I and E are the flows, what are the variables? Do we have any per capita rates, essentially, that are analogous to the per capita rates that we've been using in the past, like per capita birth rate and per capita death rate? Is there anything analogous in the classical metapopulation model? And those rates would be per patch rates now, because patch is the essential unit that we're modeling. We're not modeling, individuals. So are there any per patch rates that we might think are more likely to be constant than the total rate of immigration and the total rate of colonization and the total rate of extinction within the metapopulation? And the answer is yes, and there are two. We have the per patch probability of colonization, that is P sub I, and P sub E is the per patch probability of extinction for any given occupied patch. All right, let's go to the whiteboard now. So we're going to do some metapopulation modeling, metapopulation math, metapopulations. And so the basic equation that we just went over was delta F, that's the change in the proportion occupancy in the metapopulation per unit time, is equal to the total colonization rate minus the total extinction rate. Now, we've already defined a couple terms. So PI is the probability of it's the per patch probability of a unoccupied site becoming occupied, all right? And then we also have P sub E, which is the per patch probability that an occupied patch goes extinct or becomes extirpated, all right? So now we're going to work with these two per patch rates, all right? So let's first think about I. So I is equal to, this is the change, the total number of, or the total rate of patch colonization within the metapopulation. And this refers to only those patches that are extinct can become colonized. So first we have to take, 1 minus F is the proportion of the metapopulation that is unoccupied, right? And then we multiply that by the per patch probability of colonization. So we take only those patches that are currently unoccupied, 1 minus F, and we multiply by the probability of colonization. And that gives us the total fraction of the metapopulation that becomes colonized in a given year. And we can do the same thing with E. E is the total fraction of the metapopulation that becomes extirpated in a given year. And that is even easier. We just take the total occupied patches and we multiply that by the per patch probability of becoming extirpated. So that's a multiplication if you didn't know. Okay, so we have I and E, so we can go back here and redefine the metapopulation change, the change in the fraction of occupied patches as pi 1 minus f minus pe times f. And that gives us the classical metapopulation model, right? So, or I should say, delta f is equal to this, all right? So that's one important formula. Now this makes an important assumption as well, and this makes the assumption that pi and pe are constants. What does that actually imply? Well, if the probability of an extinct site becoming colonized is constant across a whole range of metapopulation occupancy rates, that means that even if the whole metapopulation is unoccupied, there's still a chance of colonization. That is, there's still some probability that a patch becomes colonized, even if there's absolutely no patches occupied. That means that the source of immigrants has to be from somewhere else. And so what this model actually is called, this is the island mainland model. Mainland model. All right, so the island mainland model says that there's a constant source of immigrants that are kind of pervading through the whole metapopulation, and that is called a propagule reign. All right, so the model that we've described here, this model here where pi and pe are constants, is called the island mainland model. It's the simplest metapopulation model, and it depends on a constant source or a mainland producing immigrants and kind of like raining them down on the whole metapopulation at a constant rate, so that the probability of extinction, the probability of colonization are independent of the total occupancy rate in the metapopulation. Now that is not necessarily realistic, so we're going to make a variant to this model, and let's just move this down a little bit. So we're going to make a variant. All right. So the first variant is called the internal colonization model. All right. And in this model, the probability of an unoccupied site becoming colonized is dependent on the occupancy rate in the metapopulation. The less occupancy, the less sources of immigrants, and the lower the chance that a site becomes colonized. So this is realistic for the case where there is no propagule reign. There's no mainland showering immigrants on the metapopulation. There is just internal colonization. So one thing that you would expect in this model would be that when there's complete extirpation of the metapopulation, when there's global extirpation, there should be a colonization rate of 0 because there are no potential sources of immigrants or colonists. All right, so we can now make pi a function of f, right? And the function looks like this: I times f. I is now a new constant, all right? When the fraction of the metapopulation that's occupied, f, is 0, pi is 0, right? And when the fraction of the metapopulation that's occupied goes up towards 100%, then the colonization rate becomes close to I. All right, that I is kind of the maximum rate of colonization in this model. And so this implies a new model. Remember, so the change in occupancy is now equal to I times F times 1 minus F minus PE times F. All right? So that's the internal colonization model. Let's make another variant, variant 2. This one is called the rescue effect. All right. Now the rescue effect says that when the total metapopulation occupancy, or F, is really low, there won't be very many immigrants floating around in the metapopulation, right? And therefore, there's little chance that immigrants can rescue a patch from extinction. The idea of the rescue effect is that when there are lots of immigrants floating around in the metapopulation, there's a lower chance of extinction. And that is because if a patch is occupied, but maybe there's only 1 or 2 individuals, there's a good chance that those individuals might die, but there's also a good chance that some new colonists will come in and rescue that patch from extinction. So it actually doesn't go extinct because the colonists offset any mortality that happens within the patch. So the more colonists, the lower the extinction risk. All right. So the extinction risk is going to be highest when the metapopulation occupancy is lowest. All right. So we can now make PE, the per patch probability of extinction, a function of F, just like we made PI a function of F. This time, we create a new term, E, and we multiply it by the extent to which the metapopulation is unoccupied. The more unoccupied the metapopulation is, the higher the extinction rate, right? And when the metapopulation is completely occupied, when F approaches, when F approaches 100%, or 1, then there is no extinction risk in this model. Now, that's not super realistic, but that's the simple rescue effect model. That's the one that Gatelli introduces. So as the metapopulation approaches total unoccupancy or lack of occupancy or global extirpation, then the extinction risk approaches E. That's the maximum rate of extirpation. And then as the metapopulation gets fully occupied, as F approaches 1, the probability of extinction approaches 0. So the full rescue effect model is delta F equals PI times 1 minus F minus E 1 minus F. That is the rescue effect. Now you could put both internal colonization and rescue effect in this model, and I won't write out the whole thing, but I'll just mention that there is a variant here. Okay. And I'll make this go back. Var 3 is both internal colonization and rescue effect. And you will be able to play around with this model in Insight Maker. All right, let's go back to the lab. All right, some of the basic assumptions of this metapopulation model, and all of these models, the island mainland model, the internal colonization model, the rescue effect model, and the both internal colonization and rescue effect model, make these assumptions. Number 1, patches are interchangeable. That is, all patches are created equal. There are no differences among patches. Number 2, the spatial context doesn't matter. The patches can be anywhere in space and the model will be the same. All right. So it's not a fully spatially explicit model. All right. There's no time lags. So everything, as the metapopulation occupancy changes, these rates of this I and E will change accordingly instantaneously. There is no lag. And finally, there's a very large number of patches. This model assumes that we can just think of the total patch occupancy, or the total occupancy of the metapopulation, this F term, and that's all that matters, because we're assuming a very large number of patches. Even when the fraction occupied is very small or very large, there's still, it stays just above zero. It never gets down to absolute zero, because there's so many patches, it's practically infinite. So those are the four main assumptions made in these classical metapopulation models. We've already gone through the island-mainland model, internal colonization model, right? In these cases, we're imagining that the source of immigrants in the metapopulation is internal to the metapopulation, which means that the probability of a patch becoming colonized or going extinct actually depends on the patch occupancy F itself, right? So we went over internal colonization, rescue effect. So island-mainland model assumes the propagule reign, where internal colonization is not an important piece of the puzzle. And we can consider this final variant where both internal colonization and rescue effect occur. This one you'll be able to play with in this lab, but it does have some interesting emergent properties. So it's kind of fun to play with. All right, what is a metapopulation? Well, we've been through this a little bit in our lecture, but the term it's worth talking a little bit about, because it can mean different things to different people and in different contexts. So the term is often used to refer to models where we don't care about abundance, where we only care about occupancy. So sometimes when people say metapopulation model, they mean classical metapopulation model. They're not talking about other types of models where we have different patches and space and we're doing models of populations. But I like the more inclusive definition, where a metapopulation is simply a population of patches that are potentially suitable habitat. We can keep track of patch abundance if we want. We can totally do that. There's no reason we should limit ourselves to only thinking of patches as occupied or unoccupied. We could actually keep track of the total number of individuals in each patch. We could even make the population stage structured. So each patch has its own stage structured, density dependent population. We could do that. We have the tools we need to do that. And later in this lab, I will give you a chance to play around with an Insight Maker model that does that, exactly that. Well, it's not stage structured, but it is, each patch contains a fully, explicit, abundance model with density dependence. Just as we can use metapopulation models to study the probability of regional extinction, and we can use classical models to do that, we can also, if we want, study the regional abundance. So that's the regional abundance, just means the sum of the abundance of across all patches in the metapopulation, regional or global abundance. And we can study the trends in regional abundance across the entire metapopulation. And that is commonly done nowadays because we have the computer power to do it. We have the modeling expertise to do it. And oftentimes that gives us a better, more satisfying answer than just knowing or being able to predict the fraction of a metapopulation, the fraction of patches that are occupied. We often care about abundance, and there's often good reason to do that. All right, so let's get started now with the lab. I'm not going to blabber on too much longer. I think the lab is fairly self-explanatory, and it should be less onerous than the last couple labs. Age structure and matrix population models are, I think, by far the most difficult concepts, and both in conceptually and in practice, those are the hardest topics that we cover. Metapopulations are a little more straightforward, and I'm not asking you as many questions here, so I think it shouldn't be as onerous. I hope. Just please give me feedback and ask any questions that you'd like using the discussion board at the end of the lecture page, or just by emailing me or reaching out to me or Megan. Good luck, have fun, and I will see you in the next lecture.